Do we get started now?
Yeah. Yep. So, okay. Welcome to CBE 3 review. I'm McCade.
I'm Tanner.
We are, or at least at one point, have been Calc 1 recitation leaders. Just kind of like a little overview of information. We're just going to go through this PowerPoint slide. It has many examples of what you will see on, or potentially will see on the CBE 3. Just like a note of concern. Please do not reference either each other or you can reference us by names. That's why we let you know what they are. But we will not reference you by name due to FERPA. We will also be recording this to put on our YouTube. However, we will not use your names, obviously, and your faces are not recorded. The only thing that is recorded is the fun little iPad. If you have any personal questions about like personal homework or like anything that's not on the PowerPoint, we can gladly address that after the CBE review is concluded. But just because we want to get through this and want to make this video as short as possible, we try to pretty much streamline it. That's about it. So let's get it cracking. So CBE 3, it covers lessons 7 through 10, which is derivatives of trig functions, the chain rule, implicit differentiation, and then logarithms and logarithmic differentiation. Excuse me, derivatives of trig functions. So these are some trig functions that you are expected to have somewhat memorized for the CBE review, or can at least like figure out, hopefully, within it. The main ones that you will be going through,
if the stylus will work.
If the stylus works, is derivative of sine, derivative of cosine, and derivative of tangent. These are extra different derivatives that you have probably seen previously, but they are not guaranteed to be seen on the test. So the top ones are like the main ones you want to study. Additionally, with our inverse trigonometric functions, you will have seen, it is likely to have seen all of these top inverse trig functions.
Or the angled ones.
Yes.
For the cosine.
Yeah. You will likely see some bit of inverse sine, inverse tangent, or inverse cosine. One thing that I would suggest personally doing, the inverse sine or inverse cosine is just the negative of inverse sine. Inverse cotangent is just the negative of inverse tangent. Inverse cosecant is just the negative of the inverse secant. So if you remember at least these top three, you can find the bottom three no matter what. It's kind of just a little cheat sheet. Yeah. So we have our, do you want to do this one?
Yeah, I can. You might have to remind me of some of these things.
You're good.
So we have for this first problem, we're just looking through finding the derivative of this function. So just looking at it, we have two functions up top. So I'm going to label this one h of x, and I'm going to label this one down here g of x, because we're looking at a product rule right here. So for our h of x prime, we're going to take the derivative of this top part. So we're going to have 3 times, and then as we saw from the previous slide, 1 plus x squared, like that. And then for the denominator, we have gx is equal to minus sine x. So now we can use our quotient rule. So in this case, our quotient rule will be h prime g minus hg prime all over g squared. So if we plug in our values for that, we're going to get minus 3 sine x divided by 1 plus x squared minus 3 tangent inverse of x times minus sine x. So we can go ahead and change that sign right there. Sorry, I'm scrunching this up a little bit. And then on the bottom, we get our cosine squared x. just like that. So this is our derivative of the function here. And then we just need to go through and plug in. Do you know how to erase on this?
Yeah. You'll go to this one and select an eraser
Oh, perfect.
of one of the sizes.
Does it like change or anything? Please hold.
There we go.
Sweet. So actually one trick that I'm thinking in part. Hang on. This is not liking. I get. Oh.
Oh goodness. Is there a back button? I don't know if there is. No.
Is that not charged or something?
No, it is. But now it's thinking my finger's the. No. Discard. It'll be fine.
Do we just tell Caroline to edit it down?
Yes. Yeah. Sorry, technical difficulties.
Okay.
And probably just run through that again.
Yeah.
Tanner, I think the left side should have cosine instead of sine.
We're gonna run through it again,
Oh,
so.
okay.
Yeah, because you put the derivative of g in the g spot,
Mm.
There we go. Okay.
and
Yeah.
also did a plus sign in between.
Yeah, we'll go through it again, so.
Okay. There we go.
Okay.
I don't know why I did that, but.
Yeah, that was weird. Okay, so for this problem, we can label our two spots so we can have h of x, and let's set that equal to 3 tangent inverse of x. And then if we take the derivative there, that's going to, it's going to be, I think it's like if you tap the screen, it decides that you're actually using your finger for some
No.
reason.
Why? Keep. And start. Gosh dang it, man.
Yeah, because you want that's what that means.
This is a great first review for me to do, Ethan.
Sorry, y'all.
This is
Okay, let's wait.
Okay, I'm gonna try.
I don't know why that works, but it does.
Okay, try to like not touch it at all.
Yeah.
I think.
Unfortunately, the only way you can like get to the other slide is by swiping with a finger. So we'll see how it goes.
jeez. I'm gonna put my hair back.
Sorry, put the things in parentheses so you can catch what's happening.
Okay, perfect. So, yeah, we can set h of x equal to 3 tangent inverse of x, and if we take the, if we take the derivative,
No.
do we have another way to do this?
Oh no, goodness.
Oh shoot, that's not the answer. That's right. I forgot.
Dude, somebody we can contact and be like, the pen don't.
Not at this time.
Not at
No.
this time, dang it.
Yeah.
Not even just calling Brent on his personal cell phone.
I don't dare do that, man.
That's fair. If we don't get one of these recorded, will they be mad?
There's from ones from previous years.
That's what I was
The first CBE review we did on a whiteboard because of the technical difficulties.
Yeah,
so-
we might need to do it on a whiteboard, possibly.
Yeah, but
Keep.
Is there some funky rule that I don't know about?
Start from current. Okay.
this one.
Gonna try one more time.
I just looked at it. One cos is 0. It's like cos, like it's like this x. Cos is pushing back sine.
Okay. Let's try just not touch.
Okay, I don't know for this.
Hopefully,
We'll see, because I didn't touch it last time.
it might just be like a dead pen, unfortunately.
I think that might be the problem.
to where it like charges for a bit when we plug it in, and then after that it's
Yeah. So so we can set h of x equal to 3 tangent inverse of x. So if we take the derivative of that,
did it stop?
yeah, it died again.
Okay, got it.
Should we just move to the whiteboard?
Well, we can try just finger.
Oh, just finger?
Yeah.
Okay.
It's gonna probably have some worse handwriting, but
That's
we're
okay.
gonna try to get through this.
It's also going to be hard because you almost have to like,
Yeah.
okay.
No.
Okay, well the pen works, but I would like the eraser. I guess we don't get the eraser.
I think it's because technically you haven't drawn anything because the previous thing.
Oh,
has
I
been-
see. So yeah, we can set h of x equal to 3 tangent inverse of x. So that means that our x prime is going to be equal to 3 over 1 plus x squared. And then if we set our denominator equal to g of x, and that would be cosine of x, that means that the derivative of x will equal negative sine of x. So one trick that I like to use too, where we're plugging in a specific function right here, is you can also go through before you plug in to use the quotient rule and just solve for each of these. So let's see, do you know what the tangent inverse of 0 is?
Is it 0?
It might be. I can figure out on a little triangle. So what we can do is we can look at a triangle and look for a function that we do know the solution to. So if you remember SOHCAHTOA, so it's opposite over adjacent, so x over 1, and that means that the hypotenuse is a squared plus b squared equals c squared.
Yeah, it's 0.
So it's 1 over x squared. And if you look at, say, cosine, you're going to be plugging in a 0. So the cosine inverse is going to give you theta of cosine, plugging in 0 of 1, cosine inverse. So when does cosine of theta equal 1? That happens at 0. So we can, so we know that that's going to be equal to 0, which is a pretty good number in my opinion. I like 0 in math. So this is equal to 0. Oh, geez. So this is equal to 0. Then we have g at 0. That one is equal to 1. Then we have h prime at 0. And that is going to be equal to, so we plug in a 0 in the denominator, so that's just going to be 3. And then if we do g prime at 0 sine is 0, so we get 0 again. So now we can plug in our quotient rule using these lovely numbers instead of all of the messy trig functions. And I think it looks a lot nicer when we do that. So you do derivative of the top times derivative of the denominator, so 3 times 1, minus derivative of the denominator times the numerator, so 0 times 0. That's pretty nice. And then it's divided by the denominator squared, so 1 squared. So that gives us 3, which was shown here the whole time. So no suspense.
Okay. Awesome. Okay, chain rule. The chain rule is the taking of derivative of any function that has like a function embedded within it. So you can think of it as how I kind of like to think of it as it's a function with a function in its womb. It's like a mother and has a baby inside. That's one way to put it, or you can just think of it as an embedded function. Meaning that the derivative of the function with a function inside is the derivative of the original function, where the inside function stays the same, and then you multiply by the derivative of the inside function. So let's use it. We have, it's asking to find the derivative of -5 of tangent inverse of 3e to the 6x. Cool. I'm going to label, kind of like in our f of g of x way, that our f of x is going to be our tangent, or inverse tangent, and our inside function is going to be this 3e to the 6x. Cool. And we can just pull this -5 onto the outside. Because it's a constant, we can pull out a constant when it's multiplied when we take the derivative. So f prime of x is equal to -5 times the derivative of tangent inverse is going to be 1 over 1 plus the inside function squared. It's going to be 3e 6x multiplied by the derivative of, oh, I forgot a squared. That's supposed to be a 2. I apologize. Multiplied by the derivative of our inside function. Can anybody remind me what the derivative of e to the x is? E to the x. So we're going to keep our inside function the same. So that's going to be our 3e to the 6x. But this one's actually kind of a little tricky. Our e to the 6x is a chain rule within itself. Because e to the 6x, that 6x is going to be its own function. Where the e is kind of like our mother function and the 6x is our baby function. So we need to find the derivative of that 6x, which is 6. Multiply by 6. So we are left with a 1 over 1 plus 3e to the 6x quantity squared times 18 times a -5.
It's gonna be 98.
90?
Yeah.
Times a -90 e to the 6x. We can then check our answer. Boom, bang, bop. It did distribute this squared inside. I left it out. Gives the same answer. Any questions on that? Cool.
Okay, so now for this function, we're kind of looking at, this one's a little bit trickier because you might think that we have 3 functions in here, but we actually only are looking at one function. That's the sum amongst all of those. And another thing too that we can note, and always do this with roots when you're taking derivatives, is to remember that the root is the same as the reciprocal power. So in this case, this whole function is to the power of 1/5. So we're looking at a function of something to the power of 1/5 and then the derivative of this polynomial. So derivative of this is going to be 1 over 5 times x to the 4th plus 3x plus e to the x, all to the power of 4/5. The reason we get that is we're subtracting by 1, so that gives us a -4/5. Negative power is the same as just putting it in the denominator, like we did here. So this is the first part of our function. And then we need to multiply by the derivative of the inside. So this one's a lot easier. If you guys want to just give me if somebody just wants to shout out the terms.
4x cubed plus 3 plus q to the x.
Yeah, perfect. Not too hard for us to remember, especially that e to the x is pretty easy. And that is, I believe, it for this function, besides now plugging in 0. So if we look here in the numerator, so we've got 4 times 0, so that's 0, plus 3. E to the 0 is
1.
1. And then we divide that by 5 times 0 plus 0 plus 1. So that gives us 4 fifths. Do we swipe over to get it to?
Yeah, you have to undo the pen. And then,
Oh, I see.
yeah.
And then,
There we
boom.
go. Just as a little note, this 0 plus 1 on the bottom is to the 4/5 power.
Oh, right.
But then 1 to the any power is 1. So we can just kind of take it away. Cool. Oh, that's a nasty number, but that's okay. Okay, so we have f of x is equal to 2 sine of inside is 3x squared minus 2. Okay, let's just take the derivative. So we're going to have f prime of x is equal to, that 2 we can just throw out on front because it's a constant multiplying the function. So that is equal to 2. Derivative of sine is cosine. Cosine. Our chain rule says that we can leave the inside of our function the same. So that's going to be 3x squared minus 2. And then we're going to multiply that whole thing by the derivative of the inside. What is the derivative of 3x squared minus 2? 6x. Cool. Now we need to plug in this nasty looking number. So we have 2 cosine of 3 times root 2 thirds squared minus 2 times 6 times root 2 thirds. Okay, I'm looking at inside the cosine. This squared and the square root are going to cancel. So we're left with a 2 thirds inside, which then the thirds is going to cancel with the 3, or it's going to 3 over 3 is equal to 1. 1 times 2 is just 2. So then we're left with 2 times 2, or 2 minus 2. So that's actually just 2 cosine of 0 multiplied by 6 times the root of 2 thirds. Cosine of 0, if we use our triangle or circle of unit circle, that's going to give us this first little bit, our first quadrant or first axis, and cosine at that is 1. So we have 2 times 1 times 6 root 2 thirds, and that is all equal to 12 root 2 thirds. Please. Implicit differentiation. Okay. Implicit differentiation is when we assume y is a variable representing an unknown function, as if it was like some sort of f of x, that we can think about as y or y prime or y double prime, etc., etc. When we differentiate both sides in respect to y using the chain rule on any terms with y in them. We then gather the terms that contain a y prime on one side and move all other to the other side. We factor out y prime and then we solve for y prime. This will make sense in a bit. In other words, we can also write y prime as dy dx or something along those lines. Just remember that y is not a constant during implicit differentiation. We have to treat it as if it was a variable. Okay, so for this example, we have find dy dx for y over x minus 3x plus 2y is equal to 0. So let's just differentiate both sides. This is going to be a quotient rule. So we're going to have derivative of the top, which is going to be our y prime, times the bottom, minus derivative of the bottom times the top, which is y. I do apologize for my finger spelling, over x squared minus 3 plus 2y prime. Derivative of 0 is equal to 0, so that's all equal to 0. Okay, now we need to separate this so we can get just the function of y prime alone. So that is going to be, I'm going to rewrite this as well. We're going to have y prime times x over x squared minus y over x squared minus 3 plus 2y prime. So I see two things that have y prime with them. That's our 2y prime, and that's this y prime times x over x squared. So I'm going to isolate that on the left side. I'm going to move everything else that's in this middle bit over to the other side. So we are then going to have, this also simplifies, so I'm going to simplify it. It's going to be y prime over x plus 2y prime is equal to y over x squared plus 3. We can then factor out a y prime on the left side. It's going to be y prime multiplied 1 over x plus 2 is equal to y over x squared plus 3. And then lastly, we can divide this chunk over to get y prime singled out. So that's going to end up with y prime is equal to y over x squared plus 3 over 1 over x plus 2. I would suggest not simplifying. I'm sure this can simplify. I just don't want to do it because it looks nasty, and especially for some of the classes, it'll either look like this, a version like it, or if you have to type it in for some CBEs, it will take all forms that are an equivalent expression. So
I would also just add that maybe something you could do here is you could multiply through by x on both sides of this equation.
you could, and
And
that
then-
would get rid of a quotient rule. That would be nice. Gets the same answer.
No, it gets the same answer.
Yeah.
It just looks different at the end.
It does. Cool. Boom, there's our answer. And it does say it's in terms of dy dx. That's the same thing as our y prime, just like a little reminder. So,
Different mathematicians using different notation.
yeah.
So for this problem, we'll just want to go through, first obviously starting off with the implicit differentiation. So we get 6 sine, or not sine, sorry. So we get 6, oh, boo.
Uh-oh.
Oh, we moved ahead.
There we go.
Okay, hopefully it lets me erase this time. Okay, so for this problem, we take the derivative. So we'll get 6, and the derivative of sine is cosine y. And we still need to use the chain rule, so we'll get a y prime out front. Then for this part, a lot simpler. We'll get a negative, so we get negative sine, so we can move over that negative to up here, combine it with that one. So we get 3 sine x, derivative of 3/2, 0. So that's what we get for our value. And then we can start by moving some points over. So if we move the 3 sine x over to the other side, we get y prime cosine y equals negative 3 sine x. And then we can divide by 6 cosine y. So that gives us that y prime is equal to negative 3 sine x divided by 6 cosine y. These also cancel and give us a 2 just here on the bottom because it's just 3 over 6. That's 1/2. So now it wants us to plug in the point. So we have negative sine, and then we're plugging in pi thirds here on the top. And then on the denominator, we get cosine of pi sixths. And what I like to do for this is I like to look at the unit circle. And I like to think, so we're looking at pi thirds. So pi thirds is going to be somewhere up here, just about, it's about a third of the way up through the half slice at the top. So that means we're going to have a higher y value than we are distance in the x direction. So this means that we're going to be looking at a 1/2 root 3 over 2. And this is the value we want. So on the numerator, we get root 3 over 2. And in the denominator, we can do the same thing, just noting we've got more x distance than y for one of these divided by a power of 6 or a multiple of 6. So we get root 3 over 2 and 1/2. So we're dividing by, oh, wait, that's not coming out right. Oh, that's my problem. We're getting root 3 over 2 multiplied by 2. So that gives us our minus 1/2 for our answer. Any questions? Sweet.
Awesome. Okay. Lastly, we have logarithms and logarithmic differentiation. Derivative of exponential functions, just as a reminder, if we have e to some power, it's going to be, or e to some function, we have e to the g of x times our g prime of x. That's our chain rule. But in terms of our exponentials, and then for any base that's not e, it's going to be a to the top function power multiplied by the logarithm of that base, and then finally times our chain rule factor, which is the g prime of x. And then we also have our logarithms. So we have the derivative of ln of x is 1 over x. Derivative of ln of an absolute value x is still 1 over x. And then derivative of a logarithm with any base that's not e is 1 over the ln of a times, or 1 over x times 1 over ln of a. Cool. So let's do this one. It just asks for the derivative. So we just need to find 1 over x and then multiply by the derivative of the inside. So that's going to be 1 over e to the 2x over 3x plus 4 multiplied by the derivative of the inside, which is a quotient rule. So we have bottom plus 4 times the derivative of the top, which is our 2e to the 2x. I apologize for that e. Minus our derivative of the bottom, which is 3 times our top, 2x, over bottom squared, 3x plus 4 squared. That's it.
Can I show a trick?
You can show a trick.
All right. So what we can also do here, because this looks mega nasty,
It does.
but we can make it look less nasty if we remember some of our log rules with this function. We can make it a lot nicer to run through. So if we remember with our logs, if we're dividing, if we have a log of something divided by something else, that's the same thing as the one thing minus the other thing. So the thing in the denominator. And then from here, we see a power here. So we can pull that power out, get 2x ln of e to the 1. And then over here, we kind of have to leave that one together because it's a sum. The natural log of e, that's a function to an inverse function, so that's just 1. So we get 2. So for our derivative, we just need to look at these two bits. So hang on, let me erase this. So our derivative here is going to be f prime of x is equal to 2 minus, and then we still have to do the chain rule. So inside derivative is 3 divided by the outside, so 3x plus 4. That's a lot nicer in my opinion to do.
Good.
Oh wait, I guess I'm almost next.
Yeah.
Anyways,
You're good.
anyways, it's still my turn.
Don't look at that.
So we can run through this function as well. This one is going to be a little bit strange because we've got a chain rule with two different functions. And then we have a product in that exponent as well. So if we break it down, we're going to, let's look at, let's call this first one right here, let's call this h of x. And let's call this one g of x, just to make our life simpler. So if we look at h prime of x, so just looking at this first part right here, we're going to be looking, so derivative of the outside is e x sine x. Derivative of the inside is a product, so we've got sine x plus x cosine x. And then for the derivative of the second bit, we have derivative of the outside is 1 over 3x times the derivative of the inside is just 3. That's nice. So those cancel, give us just 1 over x for our derivative. And now we can apply the product rule here. And this is going to look really nasty. So we have e to the x sine x times 1 over x. So I'm just going to write it like that. And then we're going to add ln of 3x times e to the x sine x plus x cosine x. And that should be your answer. So
It's big. Okay. And then lastly, we have some logarithmic differentiation. This is for when a derivative has some sort of function in the bottom and it's raised to a function power. It's just a very good integration technique that can help you simply solve it. There are some others, but they're not as nice looking. So you take the natural log of both sides. You can then use some logarithmic properties to then change how it looks so the derivative is easier to take. Differentiate both sides, solve for dy dx, kind of like what we did during implicit differentiation. And then remember that at the start, we had a function called y. So later, you'll see when our final version has something times y, we can then do a replacement of variables with our original function. And then these are some important logarithmic properties. The one that I would love to point out the most is this guy. The log of the something on the inside to some power is that power multiplied out front of the log of the something. Cool. Okay. Find the derivative of the following function. F of t is equal to 3t plus 8 to 3t. So I'm going to call this is equal to y. 3t plus 8 to 3t. Okay. I'm going to take the log of both sides, specifically the natural log, just because the derivative of a natural log is way more nice looking than a different base. Although it would still work out with a different base, it would just not look as nice. So ln of y is equal to ln of our 3t plus 8 to the 3t. I am then going to use one of our logarithmic properties that says I can pull this 3t out front. So I'm going to erase and put that 3t up front. Okay, now I'm going to derive. So that is going to leave us, derivative of the left side is going to be 1 over the inside of our function times the derivative of the inside, which is going to be our y prime or dy dx, times, then we have a product rule. So it's going to be the first times the derivative of the second. That's going to be 3 over 3t plus 8 plus the second ln of 3t plus 8 times the derivative of the first, which is 3. And then I want to solve for y prime. So y prime is equal to this whole expression times y. So we're going to be left with, it's going to be 3t, or 9t, 3t plus 8, plus a 3 ln of 3t plus 8, all multiplied by y. But if you remember, y is equal to this 3t plus 8 to the 3t. So we multiply by 3t plus 8 to the 3t. Cool. And I really hope that expression says the exact same thing.
It does.
It does. Brilliant. Awesome. Okay.
So just one thing I wanted to point out on this previous slide too is if you remember a bit, oh, don't zoom in. If you remember a bit back for our derivative properties here, we have that the derivative is your base to the power of the function times the original function's base times the derivative of your function in the power, which is exactly what we did, but that's kind of a lot to remember in your head when you're solving these. So it's a lot easier to just run through this process instead of trying to memorize and run through that. So we can do the same thing here. So we'll take the natural log of both sides, just letting this equal y to make things easier. So we have ln of y is equal to x squared minus 4x plus 1 to the 3x, natural log of that. And like we did before, we can take and move this out front. So we get 3x times the natural log. We can use our implicit differentiation, like we saw last time, that's going to be y prime over y. And then on this right side, we're going to get 3 ln of x squared minus 4x plus 1. And then I'm going to come down because this one's going to be a lot bigger, plus 3x times, and then we will have x squared minus 4x plus 1, and that will be divided by, and then we put the derivative up top, so 2x minus 4. And then we move the y back over, so we get our final answer of y prime is equal to x squared minus 4x plus 1, 3x, all times 3 natural log of x squared minus 4x plus 1 plus 3x times 3x minus 4 over x squared minus 4x plus 1. And that should be your answer. And that looks right to me. I'm going to hope it's right. Oh, I put a 3x. That should be a 2. But yeah, if you just remember how to do that derivative, it should be not too bad. So if you need any other resources, there's the Aggie Math Learning Center. You can also visit usu.edu/math/AMLAC, AMLC more specifically, for more videos, resources, tutoring times, and Recitation Leader office hours.
Additionally, like on that website is recordings of these CBE reviews from previous semesters and previous years. So if you want to go through this again, because you're not remembering everything here, you're welcome to watch those videos again. So thank you for coming. Yeah.